Hello everyone, myself Hemant Gowdaji from Department of Information Science Engineering, studying in Sri Venkateswara College of Engineering. Today I am going to explain you about the superconductors. Superconductors are the materials which offers zero resistance to the flow of current when it is cooled down below critical temperature, leading to extraordinary electrical and magnetic properties. Let us understand by some more examples considering 2 points A and B where A is a power station and B is the house. Case 1. If power station has 100 ampere current and has started transferring current through copper wire, then at B only 80 ampere is reached. Then the current loss is due to the copper because copper has some internal resistance due to which it opposes current to flow, which causes heat and which dissipates into electrical energy in surrounding, which is loss in electrical energy. In case 2, we can see that we can consider that point C as a new point which is the same distance from the power station, but current as is transferring through silver wire. It has got 90 ampere, which means the silver opposes less current flow than copper, due to which heat dissipation is less and energy less energy is produced. In case 3, we see that consider point D, which is a new point uh, from point A. Which got 99.99 ampere because the conductor which is used as is zero resistance, due to which there is no opposing the current flow of, therefore no heat is dissipated and hence no electrical energy loss. We all know that R resistance is equal to rho L by A, where rho is resistivity and L is length and area is denoted by A and R is resistance. From above equation, we can say that resistance is directly proportional to resistivity. Therefore, we can say that resistance and resistivity is 0, as V is equal to IR, that is voltage is equal to current into resistance. As V is equal to 0, superconductor is the material which flows current in zero potential because resistance and resistivity is 0. What is meant by superconductivity? The phenomena of losing the resistivity when the conductor is kept below the critical temperature, that is critical temperature, is known as superconductivity. It has properties is zero resistance and perfect diamagnetism. Zero resistance. Superconductors allow electricity to flow through them with absolute no resistance, unlike normal conductors. Perfect diamagnetism is nothing but they expel magnetic field completely, a phenomena called the Misner effect. Historical discovery of superconductivity. In 1911, Heike Kamerlingh Holmes discovered superconductivity while studying the properties of mercury at very low temperatures. He observed that the resistance of mercury dropped abruptly to zero below 4.2 Kelvin, as shown in the graph. The point is 4.2 is marked as TC, and this groundbreaking discovery opened the door to a new era in physics and technology. Properties of superconductors. Zero electrical resistance, that is no energy loss during electrical conduction, enabling efficient energy transfer. Perfect diamagnetism, that is expulsion of magnetic field leading to a levitation and magnetic shield application. Flux quantization, that is magnetic flux can only exist in discrete units within a superconductor. Superconductivity depends on three parameters, that is temperature, magnetic field, current density. A superconductor is a material that exhibits zero electrical resistance and expels magnetic field when cooled below critical temperature. One example is yttrium barium copper oxide, that is a high temperature superconductor used in applications such as MRI, power transmission cables, and particle accelerator for its ability to carry large electrical current without losses. Let us talk about the temperature dependence of resistivity in superconducting materials. In superconducting material, the resistivity or electrical resistance exhibit a unique technique dependence. At temperature above critical temperature, the resistivity behaves conventionally, increasing with temperature. However, the temperature approaches the critical temperature, the resistivity sharply drops to almost zero. This phenomenon is known as the superconductivity transition. Below the critical temperature, superconducting materials enter a state of zero resistivity and exhibit perfect electrical conductivity. This behavior is attributed to the formation of the copper pairs, which are a pair of electrons that couple and move through the lattice without scattering. That is, no movement or no collision in the lattice. The temperature dependence of resistivity in superconducting materials is a key characteristic that distinguishes them from normal conductor where resistivity increases linearly with temperature. It is the unique property that enables remarkable technology application of superconductivity in various fields. In normal state, resistivity decreases linearly with temperature following a typical metallic behavior. Transition to superconductivity at critical temperature, resistivity abruptly drops to zero, indicating the one set of superconductivity. Superconducting state, resistivity remains zero below the critical temperature, allowing the losses for the electrical current flow. What is meant by critical temperature? The temperature at which resistivity of a material becomes zero is known as critical temperature. The temperature below which a material becomes superconducting is also called as critical temperature. In normal state, material exhibits typical electrical resistance. In superconducting state, material exhibits zero resistance, allowing for lossless current flow. Factors affecting critical temperature is material composition, that is different materials have different critical temperature. Pressure, that is increased pressure can raise the critical temperature. Magnetic field strength, that is high magnetic fields can suppress superconductivity. Applications of superconductors, that is medical imaging, that is MRI machines utilize superconducting magnets for high resolution imaging. High speed trains, that is magnetic levitation trains, use superconducting magnets for frictionless travel. And third one is energy storage. Superconducting power grids can efficiently store and transport energy. What are the limitations and challenges? Cryogenic temperatures, that is most superconductors require extremely low temperature to operate. And second one is cost and complexity. The technology for producing and maintaining superconducting system can be expensive and intricate. Limited material availability, that is developing new superconducting material with desirable properties remain a challenge. Let us conclusion and future outlook. Superconductors hold immense potential to revolutionize various industries from medicine and transportation to energy and computing. Despite challenges, ongoing research and development are paving the way for the practical application and brighter future. Thank you.